Steel box straddle caps are categorized as fracture critical, meaning that they may require stringent designs and hands-on biennial inspections. Researchers at the Center for Transportation Research worked with TxDOT to develop a comprehensive design methodology to remove this fracture critical designation on the caps.
Straddle vents are supported by two columns on each side and are commonly used in congested urban environments. And steel straddle vents are fabricated by welding plates together to create a box. These types of structures are classified as non-redundant steel tension members, which require a federally mandated in-depth hands-on inspection every 2 years for the life of the structure.
Every 2 years, the state has to put a lot of money and time into investigating these. So what we were trying to do is develop details that gave us added redundancy in those systems and can then be labeled as we call them a non-fracture critical, but the term we use now is related more to whether it's a redundant member. And that's what we were able to kind of do in our research, is look at different details that we can use on these steel box straddle caps to try to get that redundancy in the system and thereby give a much more efficient structural system from the long-term maintenance perspective.
Nationally, there's been a lot of research on non-redundant steel tension member bridges, but there was not any research on developing these types of redundant details for straddle vents.
These were what we call full-scale laboratory tests, and we also did parametric finite element analyses to then develop, design methodologies. But the laboratory tests were somewhat unique in that they were full-scale steel box straddle caps. But we wanted to simulate a brittle fracture on these. So the way you can get a material, steel is a very ductile material, but in order to get it to behave in a brittle fashion, we can cool it down. And what we do is use liquid nitrogen to do that. So we were able to cool down the steel box caps in a region where we introduced a defect, by grinding a defect in, cycling it to grow what we call a fatigue crack. Then we cooled it down to about minus 200 degrees Fahrenheit, loaded it very quickly to initiate a brittle fracture. And then we looked at the performance of these different details and their ability then to support what we would call the design load or the redundancy load that we would have to carry in a safe fashion. Those tests then provided valuable data that allowed us to then validate detailed or refined finite element models that we could simulate that behavior computationally and look at a much wider range of geometries then. That allowed us to then go in and develop a comprehensive design methodology so that designers can actually take this and actually relatively simply incorporate this into design.
I think the most important research finding came from the study of two different concepts for these steel straddle vents. So one concept for the straddle vent was fabricated with post-tension bars, and then the other concept was fabricated with a bolted bottom flange. So this project demonstrated that if the steel straddle vent is fabricated with that bottom flange bolted to the webs, that it provides sufficient capacity in the faulted condition. So due to that bolted bottom flange connection, the simulated fracture didn't propagate through the entire member. And so this approach allows these types of structures to be designed as internally redundant, therefore eliminating that costly hands-on inspection.
For more information and to find the publication for this project, please visit the TxDOT Research Library at the link shown below.